All right, continuing off from yesterday. Yesterday we started our Pythagorean theorem notes, just kind of talking about what is Pythagorean theorem, who created Pythagorean theorem, and how we utilize it. Today we're going to do some examples of how Pythagorean theorem is used with right triangles. So we're starting with example 1, which reads, a right isosceles triangle has legs 6 meters long each. Find the length of the hypotenuse to the nearest tenth of a meter. In order to do this, we have to start by essentially drawing our triangle. It doesn't have to be perfect. I'm going to say that's my 90-degree angle right there. Isosceles triangle means that two legs are the same length, and we knew that the legs were each 6 meters. So I've got 6 meters, 6 meters, and then I do not know the length of my hypotenuse. So I'm going to put a variable x there. And we're going to utilize Pythagorean theorem. So Pythagorean theorem tells us that a squared plus b squared is equal to c squared. So where a and b are my leg lengths and c is the length of my hypotenuse. So I'm going to plug in what I know. I know that one of my legs is 6 meters, so 6 squared, plus my other leg is also 6 meters, 6 squared equals, I do not know the length of the hypotenuse at this time, so I'm going to leave that as c squared. And let's start simplifying. 6 squared is 6 times 6, which is 36, plus 36 is equal to c squared. And then now we can utilize our calculator. So 36 plus 36 is equal to 72. So 72 is equal to our hypotenuse squared. Now, to get c by itself, we have to use inverse operations. And the inverse of a square or an exponent of 2 is to take the square root. And if I take the square root of the right side, I have to take the square root of the left side because we have an equation. What you do to one side, you have to do the other. So on the right, a squared and a square root cancel, and that tells us that the square root of 72 is equal to the length of the hypotenuse, to which then again, we use our calculator. As a reminder, the square root is in blue ink above the x squared. So I click second x squared. I'm taking the square root of 72. Best practice is to always click the right arrow to get out of the radical whenever you're done. And it tells us that that number is approximately 8.485. It wants it to the nearest tenth, which is one number after the decimal. So I'm looking at this, I got 8.48. I'm using the second number to help me round. It is greater than 5, so I'm going to round up, which means that my hypotenuse is approximately 8.5 meters. I said approximate because I rounded. Okay, so that was solving for hypotenuse. Our example 2, we're actually going to be working backwards, and this time we're going to be solving for a leg. So I have a right triangle, and I knew that I was solving for a leg because our legs form the right angle, and the hypotenuse is always directly across from the right angle. So I know that my hypotenuse is 13. I know one of my legs is unknown and my other leg is 8. So Pythagorean theorem is a squared plus b squared equals c squared. And I'm going to plug in what I know. I currently don't know the length of a, so I'm going to leave that as a squared plus leg b is 8. So 8 squared equals, and this time I know the length of c. c is 13, so 13 squared. 8 squared, 8 times 8 is 64. So I have a squared plus 64 equals 13 squared, which is 13 times itself, which gives us 169. Now, in order to get a by itself, I need to isolate that variable, and I'm going to start using inverse operations. I want to get rid of this plus 64. So to get rid of it, I'm going to do the opposite, and I'm going to subtract 64 from both sides of the equal sign. And that leaves me with a squared is equal to 169 minus 64. 169 minus 64 is 105. So I have 105. And then now, similar to the previous step, I'm going to kind of move this up here so I have more room. So a squared is equal to 105. In order to get a by itself, in order to get rid of that exponent of 2, I have to do the inverse, which is to take the square root. And I have to take the square root of both sides, which tells us that a is equal to the square root of 105. So coming back to my calculator, the square root of 105 is 10.24695, etc. Rounding to the nearest tenth is one number after the decimal, so I use the second number 4, which is less than 5. That tells me I'm just going to cut off the rest of the number. So we're going to be using 10.2. So my A is about 10.2. So I have 10.2 feet. Now, a big key here is reminding ourselves that whenever we're solving for a hypotenuse, we used addition. But whenever we're solving for a leg, we actually end up using subtraction to solve. So continuing back on to the back side, here we're looking at other ways that we can use Pythagorean theorem. I'm going to start underneath where it says try it, where it says, is this a right triangle? Now, in order to identify if 3 lengths form a right triangle, we can plug the lengths into Pythagorean theorem and see if it ends up being true. You have to remember that your hypotenuse is always the longest length. So looking at my numbers, I have 8, 10, and 16. 8, 10, and 16. I know 8 is a leg, 10 is a leg, and 16 is a hypotenuse because 16 was the largest number. So now, Pythagorean theorem, a squared plus b squared equals c squared. I'm going to plug these numbers in and see if it ends up being true. If it is, it's a right triangle. If it's not true, then it's not a right triangle. So I have a is 8, 8 squared plus b is 10, 10 squared equals c is 16, so 16 squared. 8 squared, 8 times 8 gives us 64, plus 10 squared, 10 times 10 is 100, equals 16 squared. 16 times itself, 16 squared gives us 256. Simplifying the left-hand side, 64 plus 100 is 164. So according to this, 164 is equal to 256. And we ask ourselves, is that true? Well, no, those two are not equivalent. Therefore, the side lengths 8, 10, and 16 do not form a right triangle. This is called using the converse of the Pythagorean theorem, where we can identify, given 3 side lengths, whether or not it will form a right triangle. Again, we just plugged them into Pythagorean theorem to see if it was true. Another way that we can use Pythagorean theorem is when given a rectangular figure or a square, we are able to identify the diagonal that goes through the figure. This is really common when we talk about TVs, because when you go to a store and you buy a 50-inch TV, that's actually telling you the length of the diagonal, which makes it sound a lot bigger than it really is because the side lengths are not that large. So here I have a rectangle, and I see there's a right angle down here, which means that directly across the other corner is also a right angle. And if I ignore this bottom triangle, I can see that they gave me 2 leg lengths. I have A is 4, B is 11, and I do not know the length of the hypotenuse. So again, A squared plus B squared equals C squared, where A is 4, B is 11, and we do not know C. 4 squared, 4 times 4 is 16, plus 11 squared, 11 times 11 is 121. Simplifying the left-hand side, 16 plus 121 is 137. To get C by itself, I have to use inverse operations. The inverse of an exponent of 2 is to take the square root, and I have to take the square root of both sides. So I know that the square root of 137 is equivalent to the length of the hypotenuse. So The square root of 137 gives us approximately 11.7. Which makes sense because 11.7 is larger than both the legs. So to wrap this up, it says the theorem works both ways. If a triangle is a right triangle, then a squared plus b squared equals c squared. But the opposite is also true. If a squared plus b squared equals c squared, then it must be a right triangle. Now, I know there's another problem down here at the bottom related to graphing. If you want to do that one on your own, you can, but we are not going to include that in the notes for today.